right? So this is the future of MR, where we want to see MR as very fast, intuitive, and quantitative. I think the major factor would be the quantitative, where you can get a number. So the radiology will become number based, not a perception based. It's look a good image or bad image, there should be a number. So that's the direction it's moving, and as an industry we're working on this direction. We want to catch up with CT in timings. We want to perform much better imaging than CT and give you more information, and take the MR not only an imaging modality but the therapy monitoring, delivering, and probably the whole spectrum. So when you talk about this, the imaging, so today's imaging, if we just see, so these are the four main pillars of imaging, and with time in last few years, it improved a lot compared to what you have seen at the beginning of your careers. So extremely high SNR images, the signal to noise ratio, you started seeing it. These images can be acquired pretty fast, maybe few tens of folds of faster compared to what you used to acquire maybe in 10 years back. And of course the fat-free images and the motion corrections become a big advancements in the industry of MR imaging. This is just an example that how fast you can do good whole brain FLAIR images, like 3.4. We want to take it to 30 seconds, maybe less. So that's our goal, and we have some strategies how we can do those work. New imaging techniques are coming up, and those are opening up so many different thoughts how we can look at our images, get information. Like one of these technique, we call it Dixon technique, where in one scan you end up with 4 different types of images. You used to see previously just one image from one scan. Now you can get 4 sets of image in one scan. Huge big information, very new, not explored more. A lot of areas in this technique we can look at what's happening. So these are mainstream radiology I'm talking about of today's MRI. These are the example like how the imaging technique got better, how the areas you can start seeing much better in new techniques. Yeah, the conventional techniques you can see how it is and how good you can see with the new techniques. So things have improved compared to what it used to be even a couple of years back. And it's changing some strategies for radiologists also. So the conventional scans, which used to be very long, 14 minutes, it's possible to cut down with that much of information to half, close to half. So it's possible, it's not impossible. So faster scans are highly possible. So when we go for the other segments, especially on the motion, and that's a big reason why our quantitative informations were not always correct. We talk about perfusion, I heard so many times, the CVB measurements. If you see that the way we acquire data, you have quite a bit blood flow between them, right? It's a 6 seconds around. So you want to have maybe 3-4 points in between. But we acquire so slow, you don't know where you are acquiring your point. So that's a big challenge. That's why the CVB measurements are always challenging to interpret. I'll show the latest improvement where we have moved acquiring 2 points in one circle. So we have made improvement. We want to be like acquire 6 points in one circle. So
can we make it a little bit interactive? Just can you show this image, which is which is dirty? Is the patient when patient is in patient's head is in motion, right?
Right. Okay. So this is the motion correction. Like when if you acquire the images when patient's head is shaking on your left hand side, right, and how prospectively MR can correct the motion to give you motion free images. So motion free is a very important step towards quantitative, towards biomarker. So these are the key pillars we started developing to reach your dream, where you want to look at. Probably just last week I was in Singapore in a Neuro Council meeting, our Philips Neuro Council meeting, and the big talk was radiogenomics. So radiogenomics, if that's the direction field is moving, then these are the building blocks to get proper information. Right. So it also has limitations, of course. So it can, so far we can do it very well in brain, also in liver, but of course we instruct the patient that how much, like probably not to move. And so if you have a good motion correction, faster scan, you always reduce the chances of these erratic motions, right? So if we can hit the CT timings of few seconds scan, we don't need to worry about this motion correction. So this is a solution for today, but we can do it a little differently in very near future. It should not be too far. Well, when globally we look at the trends, so especially in neurology and oncology, and the needs are very simple. We need to improve our clinical indications. That means your biomarker or the information, right? So that's the global need for any advanced diagnostics tools, right? So this is the ASL which was getting discussed, and this is called pseudo-continuous ASL. So ASL is a big area of research, and the pseudo-continuous ASL technique was introduced a few years back to address the signal to noise, which used to be very poor in ASL. So far it works in tumor areas, but it gets very difficult with elderly people, stroke patients, because their blood flow are quite different, which I was mentioning just a few minutes ago. And this is a technique has a lot of potential, but still needs a lot of research. So tumor, looking at a tumor in a non-contrast way, non-contrast perfusion, this is somehow it's applicable, but it needs to get much more quantitative. We need to understand these blood flows much better than what we understand today. Diffusion is a big area, and I will show some of the examples of some of our very latest works, which we just submitted for a MRI conference. It's called ISMRM, International Society for Magnetic Resonance and Medicine. So those works, some of the slides I will show. So the new sorts of diffusion to give you much nice information for challenging areas. And these information previously were totally lost. So many diffusion studies used to happen previously, but unless these new techniques were there, a lot of diffusion information was lost. The big challenge was when you go very high B value diffusion, you have distortion, you have a signal to noise reduction. So those need to be answered, right? And the different techniques has been proposed, and this is on the right hand side. You can see this is one of the newer techniques which has been introduced. Of course, we also worked on the high B value diffusions to address the distortion issues, especially in the body areas, and of course DTI to go much higher direction to look at the brain connectivity and everything. This is a very interesting slide. I just put it here from one of the interesting work. It's a whole body M-Dixon, post-contrast M-Dixon and diffusion. And this paper, when it came out, you can see how good metastasis is picked up by combining these two techniques. So you get the diffusion information and also the anatomical information of the post-contrast T1 generated by Dixon. The whole body Dixon scan takes hardly 2 minutes. I think less than 2 minutes. It's I think around 15 seconds per station, and you have the diffusion scan. So these are the technique which can challenge even the PET. So you are working on very high specificity of imaging technique also, which diffusion used to suffer. So these are the newer approach where people started taking to see like how these newer techniques can be used. And the big setup study came out in the infections from the same group. And the infection, the fun part, it's not only in one area. If your patient come with a TB in brain, it will have some nodules in whole body. So whole body MR for our country could be another direction to look at what's there. So these are more mainstream. Of course, fMRI for neuro group, which has been there, getting into routine practice more often, and I think radiologists can comment on that. And just put a couple of examples where in this, I think it's a epilepsy study, Hinduja Hospital, they have done it. And they have also looked at the change in, I think, the speech area in epilepsy, and also looked at the corticospinal tract. And this is becoming a routine for lot of centers to study like what's happening for those patients before they are sent for neurosurgeons for surgeries. More interestingly, some of the groups are looking at how we are learning our Indian languages. And you can ask like why Philips has some interest in it? Because these are the kids who are autistic children in India. We have hundreds, thousands of study from West. How many studies we have in India? Very few. We don't know how do they learn. And what are the findings from this National Brain Research study? Their learning pattern is quite different, because our learning method in our languages are quite different. It was done in Devanagari. I don't know what would be the outcome if it's done in some other language in South. So these are very interesting areas to look at, like how our kids are learning. Well, in the post-processing side, so many tools came in, and the perfusion I was telling, we call it a T2 star perfusion and DSC. And you can, these are just one-click post-processing these days. So the informations could be there. Spectroscopy, of course, a lot of people look at spectroscopy as looking at the metabolites, maybe biomarker. I'll give you an example in few minutes. These are all routine one-click post-processing to see like how good are the additional information you can get, and of course the MR permeability to look at your K-trans, KEP, VP sort of parameters, which are more interesting for neurologists and neurosurgeon to look at the permeable or the vascularity of the tumor. So these are all now routine. So we can give lot more information in terms of what we can provided you. We could have provided you even 2 years back or 3 years back. So these are all routine.
I wanted to ask you, the K-trans is available now on neuroperfusion?
Yeah.
Because we have specialist Dr. Surya Prabha.
Yeah.
She wanted to do the epileptogenicity of neurocystic
Yeah.
by looking at K-trans values.
Sure.
Ma'am, do you have any doubts about this?
Let me go through it. I'll explain even newer approaches of K-trans, right? So well, fMRI, the bold processing, is also very much one click. You don't need a physicist to sit down and work for you. So these are all the tools and building blocks we have put together, right? Very interesting area is the resting state fMRI. So this is also part of this routine practice, and can be evaluated to understand like what happens to the blood flow, maybe to the tumor area. Maybe it may be better than ASL. We don't know yet, right? So this is a routine package, has a lot of opportunity to explore and understand. So next few slides, these are innovation slides, and we work with you. You will see a lot of different centers name, and these are all work in progress. So I have to put a disclaimer that I don't promise that any of these will ever become a product or when it will become a product. It may become a product, may not become a product. So product has no relation with research. So product is more of a marketing decision and research is research. Change in dimension in neurography, how we used to visualize your nerves. You can see like how good you can do compared to what you used to do even few, I think you're still doing today, right? This is not available as a commercial package, but this can give you really, really precise information to look at the nerves, the brachial plexus, the lumbar plexus. And these things, if you compare it with the latest techniques which are available at the scanner, the diffusion weighted based techniques, you can easily see the difference. And we played with it in India, and we came out with much interesting way to use this neurographic technique with Dixon acquisition. So you can see how beautifully and how long of a track you can see. So this is a very new approach. This is something we have sent to this ISMRM this year, and this is a very new approach to look at how good you can visualize nerve. And you can come up with a lot of ideas in image processing. You want to look at nerve compressions, etc. Feel free. Now you have a better image to play with it. So we are improving, where we'll be very interested to join with you how you can extract more information with the tools available, the imaging techniques available today. Even fMRI acquisitions, something is called multi-band. So this is a new sort of sense acceleration where you can apply in not only in single slice, but in multi-slice together. It shortens up your scan times, and this opens up a new area of looking at brain fiber tracts. This image, when I was doing my postdoc, used to take around half an hour to 45 minutes to acquire. This is a 5 minutes image, the whole brain fiber tract. So you can look at the whole brain connectivity. So these are the big improvement we started making, and to bringing them in a real world. Interesting approaches with different techniques has been taken, more towards your biomarker idea. It's called T1 row imaging. We heard T1, we heard T2, this is T2 star. This is T1 row, something totally new, right? It's also a T1 acquisition, but it's a little quite different. But this is this one example where this T1 row imaging has been applied to look at the amyloid plaques, Alzheimer's disease, and all sort of things. These are very new techniques getting explored. New types of angiography, the Dixon-based angiography, moving from the traditionally the way you used to do. But and this is the other model. We are very interested and working very closely with Dr. R.K. Gupta in this. And whatever I showed you previously, the commercially available perfusion, the main problem with that, the model used there is called TOPS model, where you have just exchange between plasma space and the permeable space. So this model adds another, is a leakage space. What is that? It's just a pure leakage. So your contrast is going out, is not getting into the equilibrium stage, and that's actually real. So how do you know it's real? So when you looked at different parameters with time, we started seeing all those supposed to be constant parameters goes high and high and high with time. That cannot be possible. Then it's something wrong with the model. So TOPS model is well approved, accepted, but there are issues with TOPS model. TOPS model you have to acquire for very long time to get into the equilibrium, 20 minutes around. So that's very hard to do, right? So this model, changing the understanding of perfusion or the permeability, so they addressed it as, if you see, this is the new model where the constant become constant and very fast. The whole acquisition is less than 3 minutes, and you end up with excellent quality results. And these are some results. You start seeing it, and the more beautiful what we noticed, when you address this leakage, a pure leakage which is going out from the system, you started seeing more heterogeneity in the tumor instead of just a big red blob. A tumor cannot be a big red blob. You'll have heterogeneity. So probably we are moving towards more realistic approach to address what's happened during perfusion. Very interesting areas. This is the ASL technique, the super selective ASL for the AVM, where you can label each and every arteries, feeding arteries, and can put them together to get the different feeding arteries which are feeding these AVM areas. These are all, and not only that, time of arrival using ASL, very nice color plots that what blood is arriving in which area, what time. So these are very interesting works are going on in different parts, and could answer a lot of your questions also. Moving towards the imaging biomarker. So our first realization were that imaging biomarker doesn't mean that you need to have a new contrast agent, functionalized contrast agent. So my training is a chemist. I worked as a NMR person first. So we, in chemistry department, that's the big thing, nanoparticles, functionalization. Actually, we don't need, we can start much simply. Because there are questions. This is a tumor, glioblastoma, with no enhancement. How do you understand? We put this permeability scan and all the permeability parameters, and you started seeing the differences. But if you just see at the routine contrast images, you cannot say like whether it is enhancing or not. Similarly, this is a low-grade glioma with high-grade focus. Very difficult to identify just from the regular scan. How we answered it, looking at again this perfusion and permeability parameter, and you can see like this very nicely the focus. You can see the different perfusion, and surrounding you're much less. So high grade and low grade mix, you started seeing it. So with this, we thought like how we can look at this contrast enhancement. Simple. So to understand the contrast enhancement, we looked at these CBV values, like how the blood flow is happening, and we started segmenting the tumors. What is the use of it? Beautiful use found by the radiologists with neurosurgeons. They know from where to take the specimen for biopsy. You know, you have all the segments, and they decide like exactly from where you want to take the biopsy to understand what type of tumor. So this is a small step towards biomarker, we'd say. This is another area where we also started looking at what's happened in the contrast mechanism in a tumor versus infection. And we found there is a big difference when you look at the leakage and the vascularity. So the difference is extremely high in infection, but well, the difference is much lower in gliomas. So this started giving us some idea exactly how contrast enhancements happen, why some tumors enhance, why it doesn't. So we're looking at or moving towards a direction where we want to have the fundamental understanding so that we understand what we are doing, how it's changing or addressing our physiological pathologies. This is another one combining two techniques. The diffusion, we looked at the ADC map and the CBV at the same time, and we looked at them in a way when the subject is going through a radiation therapy. So these are all follow-up scans. You can see this is a positive response. Your ADC maps, the higher values are going up and up. So that means your cells, the radiation therapy is working, right? And if you look at the perfusion area, and this is not the regular perfusion, this is with the latest model where we can acquire 2 data point at least today within one circle. You can see your vascularity is decreasing. And this is a very nice trend. It's a very short study, still today, just 10 patients we have looked at. They're following very well. So we want to do it in a much larger extent and wanted to see like where it fails, what happens in the radiotherapy and why it's failing. But the basic hypothesis is actually matching. We had issues with previously model of perfusion, and that could be the main reason why we're not able to see these sort of very nice results. So things are improving. Dr. Ramon mentioned the new black blood method of looking at the plaques. So I quickly picked up a few slides to put it here. So black blood, so blood is black, right? And you can see how good you started seeing the plaques. Not only that, you'll have more exciting part, how good you can visualize in 3D. So this is a totally different technique from what is getting used today. This is that same technique we are using for the neurography technique, the latest neurography what I have shown. So this is the latest technique, and people are working, especially Japanese are very active in this field, and how beautifully they have demonstrated the plaques. This is one of the interesting biomarkers people have looked at using spectroscopy. It's the editing spectroscopy, and they looked at the results over time with therapy, that what happens to this marker, this 28G, and it shows some promises. So people are taking multiple approach to look at or identify what could be the right imaging biomarker. This is one of my favorite area, and I worked on this area looking at the GABA. And the GABA is playing so much of role in brain, right, starting from epilepsy to schizophrenia. And we worked on generating GABA signals during scanning, which is not possible in regular way. And of course the GABA map, GABA and glutamate map of whole brain. More interesting, very new, is the amide proton transfer technique. So our brain has, when there are stroke or tumors are there, a lot of different proteins comes into play. We heard that in the first talk, right? So the idea is like, can we use some of these amide proteins to look at what happens to these proteins, right? And there are techniques, it's the APT technique, and you can start seeing the differences in
next speaker. So.
Yeah, sure. The APT and for the stroke, and also for the imaging of tumor. So there are glycocysts, so many different type of techniques. So amide, not only amide protein, there are like at least 15 different type of this technique has been proposed, where these techniques can be used to look at these different proteins contribution to a tumor or stroke. These are a few examples, and I'll just go it fast. I will probably not touch this area. And just to give you an overview, like where the it coming towards matching with radiotherapy and planning. And the future of radiotherapy is right here. Instead of CT, which we used to do still today, CT and MR merging together to generate your DRR, we're not too far where we can do the whole thing. So this is today's setup, and still you need the CT. We're not too far that we can do the whole thing just using MR. And how do we do it? This is an example. Again, we take advantage of this Dixon technique and something it's called ultrashort TE, which gives you beautiful bone information in MRI, which was or which is still missing. So once you get the full bone information and all the information, you can generate your DRR. So it's not too far that radiotherapy planning will be only MR based. CT we can remove fully. And the big project we are into is the treatment delivery, where we are putting LINAC inside MR. So the whole treatment delivery will be MR guided. And this is the first system prototype has been installed in Utrecht University in Netherlands. And there's a big project to show you like how the field of MR is changing from today's environment. And this is the very near future: diagnosis, planning, treatment, and therapy follow-up. We're not too far. We're very close. With this, I thank you for your attention.
Thank you very much, sir. Excellent and lucid. Of course, a lot of us need to catch up with some of the terms in MR, the acronyms and things, but definitely Dr. Suvarna must have, her eyes must have lit up